Can we go back to like some of these early chapter 4?
Yeah.
Because I was looking at those last night and I was like, I don't remember.
Yeah, I didn't even, when we came back from break, I started by reviewing chapter 5, so we haven't reviewed that, so we'll definitely do that. I put this back up here, the molecular shape stuff, just to remind you guys, this is kind of, you can kind of memorize what you see here and infer everything else. So look at the first one under carbon, tetrahedral 109.5. That's a situation when carbon is connected to 4 different atoms completely, 4 different separate atoms. Carbon can make 4 bonds if it's connected to 4 different atoms. That's tetrahedral 109.5. Carbon can be connected to 3 different atoms. Just one of those will be with a double bond, and then 2 with single bonds. That's what we call trigonal planar, 120 degrees bonding angles. And then the only other 2 ways you'll see carbon is a triple bond to one atom and a single bond to another, connected to 2 different atoms. That's linear 180. And another thing that carbon can do, it can connect to 2 different atoms with double bonds to each one. That's also linear 180 degrees. And also realize that below carbon on the periodic table is silicon. I can replace the C in all of these and just write Si, and it's all. Everything below carbon does exactly what carbon just did. Next over is nitrogen. Here's the situations you'll see nitrogen. Nitrogen can make 3 bonds. If it's connected to 3 different atoms, then we call that trigonal pyramidal, 109.5 degrees bond angle. One other way you might see nitrogen is double bond to one atom, single bond to another atom. That will be bent at 120 degrees. And anything below nitrogen, phosphorus, on down to the metalloid. So I could replace that N with a P, and it's all still true what you see on the board. So if you just memorize this handful of stuff, then you don't have to think too deeply about molecular shape. And of course, there's oxygen makes 2 bonds. If those 2 bonds are connected to 2 different atoms, it's bent at 109.5 degrees. So I just wanted to put that up there as a reference. And what we'll do is we'll start by reviewing chapter 4, which is where this stuff pops up. Get the camera reset. So I've already got it open to the molecular geometry quiz. Let's see. Which one of these is incorrectly? Do you know which one of these is incorrect based on what you see here? If you memorized this, which one of these is wrong?
Trigonal pyramidal.
Yep. Trigonal pyramidal. Also note here that when you see structures like this, they're not always giving you the full Lewis structure. For it to be a full Lewis structure, it needs the lone pairs put on there. Also known as the non-bonding pairs. That's this and these 2. They're there, they're just not always drawn on the thing. So just don't forget that you're seeing that. But predict the bond angles around the carbon atom. So here's the carbon atom. And it's probably worth stressing that it's not always going to be drawn exactly like this. The orientation won't be exactly like this. But if you look at that and think to yourself, there's carbon connected to 3 different atoms, double bond to one of the atoms, single bonds to the other 2. That's what should narrow you in to that. Makes sense. So there's kind of some 3-dimensional thinking and 3-dimensional geometry here. But if you'll just memorize this, then you don't even have to think that deeply about it. You just memorize what's connected to what, and you can narrow down to what's what. Maybe the difficulty with some of these would be, so pH 3, you're given P, and there's 3 H's. I'm going to go ahead and draw them the way I want. There's the Lewis structure of hydrogen. How many valence electrons are in phosphorus? you're really looking at it here. Phosphorus is below nitrogen. Oh, I should have said sulfur is the same as oxygen. But 1, 2, 3, 4, 5. So I would do this. You need a lone pair and then 3 atoms like that, and then you can connect these together. That's the pH3 diagram. So what would the molecular shape be for that? Exactly like this, trigonal pyramidal. What's the bond angles for? So like I said, you're looking right at it. If you can memorize this, then all these questions just fall off the page. What are the bond angles for tetrahedral geometry? 109.5. You see it right there on the board, right? If you just memorize that little set, you can do these without any trouble. Estimate the bond angles around sulfur. So it's bent. I didn't talk about doing roughly 109.5, so just skip that one, number 6. What is the molecular shape around nitrogen? Here's nitrogen connected to two different atoms with a lone pair on it. So what's the shape for this one? That one is bent 120 degrees. Do you see it? So without going back into why these shapes end up the way they are, you can just memorize them like this. So I think the rest of this just falls off the page, I think. I won't ask you that. That's just some vocabulary. Each thing around the atom is a group. That's a group, that pair. These 2 bonds together are a group. This is a group, but that's just vocabulary. Don't worry about that. You guys have any questions on this? It's just a matter of identifying the shape. BF3. Well, let me show you how you would make these small molecules the same way I did this one. Number 11, BF3. I'm going to go ahead and draw them where they should be. But here's your Lewis structures. And you can infer the fact that since fluorine's only ever going to make 1 bond, in boron, it's got 3 valence electrons, so you start counting around like this. So there's the boron molecule. I probably should have done this. Going across the periodic table back this way. You're either going to see boron like that. This one's, and this one's. Trigonal planar 120 degrees. So by the time you connect these together, you have this situation. So that's the first one. It's asking which one is incorrectly paired. So trigonal planar is correct there. Sulfur, H2S. You've got S, and it's just like, I'll draw it the same way. It's just like oxygen. It'll be like that, and with 2 H's. You've got that, and it's these 2 that pair. So what's the shape there? That's bent at the tetrahedral angle, and they've got bent, that's right. CO2, carbon, oxygen, start like that, you make your first bond, and now you've still got these dangling, but these two can come together and make their bond. And these two can swing around here, make their bond, so it's like this. Linear. CBR4. So you've got C that looks like this, and BR, that's below fluorine. So this series of dots should look like fluorine over there. Bond, oh, it's BR4. Bond. So you have this tetrahedral SO3. That one is going to involve a double bond, but that's going to be the wrong one just by process of elimination. Starting with phosphorus on the periodic table and anything bigger, you can actually have more than 4 bonds to that central atom. Another way of saying that is you can have more than 8 electrons around it. Notice, not these, but all of these have 8 electrons around it. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But by the time you get to phosphorus, you can have more than 8 around it, which would be the expanded octet, the way we put it. So it's got to be that last one that's wrong here, because we just verified the other ones. And sulfur is going to have the expanded octet here, I think. 3. If it's not charged, it has to be. Okay, this one's a little more involved, but how many of these do you see that have the trigonal-planar geometry? You can ignore the hydrogens; those are never going to come up in this type of question. What is this oxygen? It's connected to 2 atoms with a single bond. So what's the shape here? Not linear, it looks linear. That tricks everybody, gets a lot of people. When these are drawn this way, they don't have to be drawn like in the correct orientation. These types of diagrams only show you what's connected to what. They're not trying to show you molecular shape. But when oxygen is connected to 2 things, that's what it is. So don't let that fool you. Those types of diagrams are meant to show you what's connected to what. They're not meant to show you geometry. I went to the trouble to make this look bent when I drew it this way for you. But it's really what you're looking at here is it's oxygen connected to 2 other atoms with single bonds. That's what makes it bent. So that's really not linear. This is really not a straight across thing. If you could actually see it, that little tiny molecule, this is not straight across, it's bent, kind of the way I've drawn it here. So that oxygen is bent. This oxygen double bond to 1 other atom, I didn't put that here because that's really a null case. Of course it's linear. It's the only thing it can be if it's connected to only 1 other thing. 2 points connected in space is necessarily going to be 1 line straight across. But no one ever asks you those questions about these. This is connected to at least 2 different atoms. This one's connected to at least 2 different atoms. If I did these down to where it's a double bond connected to 1 atom, it's like a null case. I guess you would say linear, but of course it's going to be linear. So you don't tend to get questions on those. These are the ones that you need to memorize. So oxygen, this oxygen, double bond to 1 other atom, I didn't even put that up here. I guess you would call it linear, but it's really a null case. How about this carbon? It's up there. Do you see it? So what is it? So there's one. This is asking us how many trigonal planars we see. This carbon is tetrahedral, this carbon is tetrahedral. There's another trigonal planar carbon. So there's two. This is bent, don't let it fool you, it's not linear. How about this nitrogen? The pairs are omitted in this type of diagram, but they're still there. There's two lone pairs on this oxygen, there's two lone pairs on this oxygen, they're just not drawn in. And there's one lone pair for this nitrogen. So we're really looking at this trigonal pyramidal for this nitrogen. Do you see that for this nitrogen? So I only counted two, so I guess that's the answer. Two trigonal planars. You guys see this? Again, if you'll just memorize what you see on the board, and I guess I should include boron, really just because it's there. And nothing else comes up in these types of questions. Molecular shape questions. So that was chapter 4. Oh, I never opened this up. I went over polarity and I never opened this up so y'all can see it. So I'm going to leave it off the test. I'll talk about polarity one more time for test 3, but it's not real hard. But since I just didn't open it for you, then I won't put it on the test. This is really simple, naming and formulas. I probably shouldn't even spend time on it. The chemical formula for this Lewis structure, I'll give you A, B, C, D, and E to choose from, but you're just looking for something that has N with 2 as a subscript and Cl with 4 as a subscript. You know what I'm saying? So N2Cl4 would be the formula for this. Phosphorus pentachloride, that's going to be P for phosphorus and Cl for chloride, but there will be a subscript 5 on the Cl. I'm just being lazy sitting here. I can write these. My own camera.
So does it matter the order, like for that first one?
It does, but I haven't given you any rules to follow, so you'll have an A, B, C, D, and E, and just don't worry about order. I won't
Okay.
mess with your head on order.
Perfect.
But so that first one would be N2Cl, Cl4, and this next one, phosphorus pentachloride, P for phosphorus, Cl5. Like I said, I'm going to get on to the calculation stuff because this is all. I didn't do nitrous, so this would be nitrogen dioxide. So nitrogen dioxide. So these are just very easy. Don't overthink these. Any questions on these? This is dinitrogen pentoxide, N2O5. I don't think there's any surprises in here. Which one? Number 9. This one? So it's just, it's di, tri, tetra, penta, hexa. For 7, it's hepta, if that one comes up. 8 is octa. 9 is non, N-O-N. And dec is 10, and we'll stop there. There are more Latin words for 11 and 12 and stuff, but we won't do those. So 1 carbon, 4 bromines, so that's carbon tetrabromide. 1 sulfur and 3 oxygens, so it's sulfur trioxide. 2 and 4, so it's di and tetra, so diphosphorus tetroxide. Dinitrogen trioxide. The problem here with aluminum trichloride is that's an ionic compound. So when you have all nonmetals, which A, B, C, and D here all have, then you name it this way we're doing. But we already went over for test one, naming ionic compounds. That should just be aluminum chloride. There's only one way aluminum and chloride can go together, and that's with one aluminum and three chlorines. Chemists know that, so you don't have to say trichloride because of the charges. Covalent compounds don't involve those charges, so you're not trying to balance charge when you have these formulas. So that's the one that's named wrong because it's an ionic compound, and those aren't even on this test. But the naming for that was what we did naming for the previous test. Okay. Should we do this? I think this is just facts about covalent bonding. Covalent bonds result from the sharing of electrons between two atoms. It's not necessarily equal. It just said equal sharing and unequal sharing. Yeah, that's what's correct. That phrasing is weird. But the unequal sharing is when you get polarity. But like I said, I didn't open that for you, so I'll put it on the next test. So we're looking for the one that's covalent here. We're just looking for the one that has only nonmetals. Potassium is a metal, lithium is a metal, sodium is a metal. HCl though, those are both nonmetals. You follow me? So that's the one that's going to have a covalent bond between the hydrogen and the chlorine. Same here, not classified as covalent. So we're looking for the ionic compound, and it's magnesium chloride. There you have a metal and a non-metal. Nitrogen has 5 valence electrons, so does phosphorus. So this one, how many covalent bonds is generally formed? So you can see there that you get 3 covalent bonds out of this. How many covalent bonds are generally formed by oxygen? You're looking at it right here. 2. If I'm going to be consistent, I should. So that's where you get your bonds. Oxygen can make 2 bonds. It can make 2 single bonds with 2 different atoms, or 1 double bond with 1 atom. Hydrogen makes 1 covalent bond, and so do all of these: fluorine, chlorine, bromine. Okay. So let's get to the mole. So I pretty much have at least one of each of these different types of calculations on the test. How many carbon atoms are in 3.85 moles of carbon? This whole section is that section where I stressed that how many carbon atoms? How many carbon atoms? Notice there's no unit here, so you number, and usually there's a unit, and then for carbon atoms, I just say C. That's what I mean by here, carbon atom. When there's not a unit, that's when you're going to use that relationship. This number, this relationship, 1 mole is this, only shows up in calculations when you have this situation. 3.85 moles of carbon atoms. You need moles on bottom. And in this case, we're talking about our label here is carbon atoms. 1 mole blank carbon atoms. And that'll give us a number, blank where a unit would usually be. When I do these, I ignore the power of 10 at first. I just take all the explicit values, 3.85 times 6.02 gives me, and now I just take the 10 to the 23 on there. Three significant figures, so I keep those three. So 23.2. Not quite in standard scientific notation, but you could go. So both of these are correct. This one's correct if you're asked for standard scientific notation. But generally, I'm giving you A, B, C, D, and E, so I'll have one or the other in the answers, and then 4 other wrong answers. So that says how many carbon atoms in this many moles. So you're given moles here, 3 moles carbon atom. So this one's asking you how many moles when you have this many. And notice 5.47 times 10 to the 26 molecules, not grams of molecules, not moles of molecules, just molecules. So that's supposed to be your key that you're going to be using this relationship. So all of them in this section are like this, just so you get used to picking it out. How many, so it's equal sign, how many moles of C2H3Cl. So you can put your equal sign and then 5.47 times 10 to the 26. Let's say 26. Blank carbon atoms. And you got the blank on top here, so you want the blank on bottom here, so it's going to be 1 mole of C is 6.02 times 10 to the 23 blank C. And if you have the fancy calculator that you can plug this in, then you do it your way, but I would do it as so that takes care of the numerical values. The blank C cancels, and we end up in moles of C, and then the rest is calculated. 5.47 by 6.02. 5.47 divided by 6.02. Calculator says 0.8637873775. My calculator says it's 3 significant figures and 3, so I'm keeping those. The 6 rounds to 8. Times 10 to the, so I'm going to move the 10 to the 23 up here, but it changes the sign. So times 10 to the negative 23, and now that's a 1. And now it's 26 minus 23, so that's 10 to the 3. See what I did? The exponent. Anybody get lost on why that was a 3? And standard scientific notation would be 9.09. So I moved it up 1. So both of those are correct, but this one is in standard scientific notation. So the 2 different ways you get this, you're given moles and you're asked how many, or you're given how many and asked how many moles. All these questions in this section are exactly like that. Anybody get hung up on any of these? Any questions? All right. So that was the mole. Now molar mass, think grams per mole for molar mass. And let's get subtle distinction here, but when you have an ionic compound, we call the formula KCl, we would call that formula weight, what I'm about to calculate. And when it's a molecule, we call it molecular weight or molar mass, but that's really just kind of a subtle distinction. But, I won't hang you up on the vocabulary, just if you're asked for formula weight or if you're asked for molar mass or molecular weight, you're looking for grams per mole. And I always do these in a standard way, same way I've done this for you before. There's a K in the formula mass and there's a Cl in the formula mass. There happens to be one of each, so I'm going to put a 1 there, and then the rest we get from the periodic table. Chlorine is 35.45. That periodic table has more decimals, but I'm going to give you this like I usually do, and we'll just use this one. So you get 2 decimal places. And the one I didn't know off the top of my head is 3910 for potassium. And of course it's times 1, so you multiply them across, now you add them up. And then you just stick a G per mole, 74.55 grams per mole. Assuming I did the arithmetic quick, I went through that kind of fast. These with parentheses don't get lost here. That's showing you there's a cobalt, and there's one of them, and you have a parentheses. You have 3 of these NO3 units, so that means you have 3, 6, 9. You actually have 9 oxygens and 3 nitrogens. And if you picture there being a 1 there with the nitrogen, then all you're doing is you're taking this number outside and multiplying it by that number. So 1 times 3, that's 3 nitrogens. 3 nitrogens, and how many oxygens? 9 oxygens. 16.00, 19, nitrogen is 14.01, cobalt. Sure, I don't have that one memorized. But you just get these off the periodic table. Cobalt is right there, 58.93. So multiply those out, add them up, that tells you the grams per mole for that molecule. You might have to calculate that en route to a bigger calculation. I'll show you that in the next set here. Okay. Different type of problem. Now we're actually using the grams per mole to calculate something. So this is saying, number 5, what is the mass in grams of 3.81 moles of pH3? First, you have to calculate the grams per mole for pH3. That is its molar mass. one P, three H's. Yeah, I remember phosphorus. Some of these have stayed in my head for 20 years and some of them just won't stay. 30.97. Add them up. It's 10 grams. Another way to write, this is 34.00 grams per mole. Another way to write that, grams of pH 3 to 1 mole. So this is this just rewritten. So it's helpful to be able to do that. And then, what was I given? 3.81 moles. So this is actually set up 81. Moles of pH 3, moles of pH 3 cancel. And it gives us what we want, grams of pH 3. That's what we were asked for. And you multiply that by that. We did end up with 4 significant figures here, but we've only got 3 here, so you go 3 significant figures for that. .81 times 34. My calculator says 129.54. And if I'm going to 3 significant figures, I'm keeping those. The 5 rounds to 9, so we have to go all the way to 30. And since I want that significant figure to count, I've got to put a decimal there. It's 130 grams. So we had this, in this case, we had to calculate the grams per mole for pH 3, and then we used that relationship to go from moles to grams. And those are the types of problems here. This one, this is just done the same way as before, but you would have to, I guess it's easiest to turn that into a formula first, or at least add up the atoms. But this is, how many carbon atoms are there? This last one.
4.
How many?
4.
How many oxygen?
4.
How many?
4.
There's 4. How many hydrogens?
7.
7. And isn't there a sulfur? No. There's a nitrogen. 1, 2, 3, 4, 5, 6, 7 hydrogens. 1, 2, 3, 4 oxygens. 4 carbons and 1 nitrogen. Times 12.01. These are from the periodic table. The few that I have memorized. So you calculate those out, you add them up, that gives you the grams per mole for that molecule. And now you can go from moles to grams or grams to moles using that relationship for that molecule. You guys good? Okay, reaction calculations. The next section of questions is on percent yield. So it's worth pointing out that when you're given an amount of a reactant and asked to predict the amount of a product, you're calculating the theoretical yield. It's just not mentioned in these problems, but that's what that is. So when you get to the percent yield section next, then we actually start calling that theoretical yield. But to do problems like this, we got 2H2, so here's our reaction, 2.
And I told you I won't make you balance these, but know how to use the balance equation, that's more important. I have to circle back for a few things. This stuff in parentheses you can ignore for now, but those G's just mean these are in the gas form instead of liquid or solid. You've got that. 8 moles of H2. 8 moles of this reacts with 4 moles of this. How many moles of water? In this case, you can use either one of those reactants. I won't ask one like this on the test. We still have to do one other thing. In that chapter. So yeah, I guess ignore number 1. Let me double check these. Okay, let's go on to 2. Notice this one gives you H2 and also amount of O2, both reactants. There's this thing, limiting reactant and excess reactant. So ignore number 1 for this section. I probably should have deleted it. So this one is only giving you one of the reactants, and you're predicting the product. Sulfur trioxide, that's the sulfur trioxide. How many moles of this product are formed when you put in 3 moles of sulfur dioxide? This is the way I want to have it. Just giving you one of those. Plus O2. So you have that balanced reaction, and you've got 3 moles. So the molar relationship here between SO2 and SO3, I'm going to put moles of SO2 on bottom. And in this case, it's really 1-to-1, but I would still put the numbers in. There's a 2 here and there's a 2 here, so there's 2 with SO2, 2 with SO3, and that'll tell you how many moles SO3 are formed. And of course, it just ends up being 3 because this is pretty simple. And that's the significant figures too, just 1. But the ones I'll put on the test have 3.46 or something. I won't keep them in neat integers like that. Okay, this one's number 4. So there's your balanced equation. And it's saying if you put this many grams of if you produce this many grams of AgCl, how many grams of AgCl are created? 85 grams of this reactant going. So this is calculating theoretical yield. Those first ones I did were calculating theoretical yield in moles. Usually we calculate theoretical yield in grams. BaCl2 plus AgNO3. Those 2 react and make 2AgCl plus Okay, 85 grams of BaCl2. I'm going to need grams. So what we need here is grams per mole for BaCl2. So we have to do this. What is Ba? 137.33. And if I add those up, I get 208.23. And now I'm in moles of BaCl2. So I'm gonna put that down here. Now I'm gonna use this. 1 BaCl2, and is it AgCl I'm predicting? Yeah, AgCl, so how many grams of AgCl? So AgCl, there's 2 of them. This wants grams of AgCl. I'm going to put moles of AgCl down here. We're looking for the grams per mole for AgCl now. So 1 mole is how many grams of AgCl? So I have to calculate that. AgCl, 1 of each. And silver, 107.87. And the rest is the math. $85 times 2 times 107.87 divided by 208.23, and that's it. And my calculator says whatever. 5 significant figures, 5, there's 2 there, so I'm really just keeping those 2. The 0 doesn't round anything, so the answer is 88. So you're relating 2 things, you need the grams per mole for both of those things, and you need that molar relationship that's expressed in the grams per mole for the first thing, molar relationship between these 2 things, and then grams per mole, or really moles per gram, just because I'm using it flipped over. You guys okay? You could also be asked for moles. If this didn't say how many grams of AgCl, it might have said how many moles of AgCl, in which case you don't need this. It's just a shorter calculation, and you could get the moles. Usually we do theoretical yield in grams, but you can express theoretical yield in moles too. But what we just calculated there was a theoretical yield. Given this much reactant, how much product do we get? That's a theoretical yield.
88 is not one of the absolute choices.
It should be 120.
What is it?
120.
Did I calculate it wrong?
You put the thing for silver into the fraction instead of adding it to the CL first.
Oh. Oh, I see. I just looked up AgCl and wrote it down. I think we're doing good on time, so I'll do it right. What is AgCl? I mean, what is Ag? 107.87.
It was 107.87 for that.
So I really needed to add those together.
Yeah. So
then we get 143.32 grams is 1 mole of AgCl. And 85 times 2 times 143.32 divided by 208.23 is 117 up there. Two significant figures. So I'm keeping those, the 7 rounds of that, so I get. So that should be an answer. There it is. Oh, it's 2 significant figures, so really I should do that. All right. So we've calculated theoretical yield a couple of times. We just didn't name it as theoretical yield. Now if we go on to percent yield, percent yield is actual divided by theoretical times 100%. So this is just like the question we were asked before. What is the theoretical yield of Na2O, this product, if 9 moles of O2 goes in? And you can tell by the answers, it's looking for grams. Like I said, theoretical yield, we almost always just go ahead and calculate it out to grams. To do this one, so we're going to need Na2O and O2 grams per mole. On the periodic table, oxygen is 16, so that would be so O2 is this. Na2O. Na is 22.99. Is that right? Sodium 22.99.
Mhm.
Two, 99 times 2. Add those up. So there, now we've got those calculated. Oh, 9.0 moles of O2. I'm not going to need this because grams of O2 isn't mentioned. 9.0. If they had given us O2 in grams, then I would have needed that, but they were already in moles. So moles of O2, and now it is, the molar relationship is 2 Na2O to 1 O2. It wants the theoretical yield of Na2O in grams. So I've got to take Na2O to grams, so that's what that's going to be. Mole needs to be on bottom. So 1 mole that should do it. That should give us our theoretical. This isn't even a percent yield problem. My calculator says we need two significant figures, so it's just that with no decimal. Did I do that right? Why does that feel wrong? That's not there. $22.99 times 2 plus 16. Oh. I calculated that wrong. That's wrong. 22.99 times 2 gives me the 44.98. I did it again. I didn't finish adding up the. Let's see if I can get the right answer here. We need to move along. Times 2 times 16.98. Now I get two significant figures. So 310. Tell me that's there. 310's not there. I'm calculating this right. One to two.
The grams per mole of Na2O is 61.98.
I transposed the 1 and the 6. Good Lord. We need to move along, Embry. Times 2 times 61.98. Now my calculation. Two significant figures. Yes, 1100 is there. It took me 3 tries. Alright, so be careful with your calculations. I'm trying to go fast here. Okay, but we want one that actually asks about percent yield. So read question 3. Here's your reaction. Same reaction as before, and it says, if we use 2.55 moles of sodium and 75.0 grams of Na2O is produced, that amount that it says is produced is the actual yield. They haven't just given us the theoretical yield. So we have to calculate the theoretical yield. Then we use that 75 grams as our actual yield. So we do it just like we did the other one, but now we've got 2.55 moles of sodium. Can I do this quick? .55 moles of Na. Now I need Na here, and that relationship is 4 Na to 2 Na2O. That should do it to give us our theoretical yield. Times 2 times 61.98 divided by 4. Calculator says 790,245. 3 significant figures. So it's these 3, so 79.0. And now we calculate the percent. Our actual yield What is the percent yield?
Actual was 75.0 grams. Theoretical, 79.0 grams. Three significant figures, so that's correct. It's unitless. Well, no, it has a percent. The grams cancel out though. Is that there? Okay, good. Yeah, so it's all about calculating the theoretical yield, the theoretical yield. And then the actual over theoretical times 100 is a simple calculation after that. All right. Energy, let's do the calculations in energy. So you're always given, again, a reaction. Let me find one that's got some. So look at this one, number 3. 3 NO2 plus H2O gives us 2 HNO3 plus NO. I've said this before, but before you do anything, you don't have to write all these out, but before I do anything, just realize it's just like those molar relationships. In this case, there's 4 energy relationships here. 3 moles of NO2, and then another one, 137 kilojoules. The sign, the plus and negative is kind of a subtle thing. I guess I would say just take the absolute value of the energy given, and then the rest is context. 1 mole of H2O. And there's NO. So this is saying 92.3 grams NO2 reacts. How many kilojoules are produced? First, we need grams per mole for NO2. And then we will do moles. NO2, this should be a 3. 3 moles of NO2 gives us 137 kilojoules. That'll do it. Oxygen is 16 plus 16 plus 14.01. So this is 46.01. 92.3 times 137 divided by 46.01 divided by 3. And I have 91. Three significant figures, 4, 3, so I'll need 3, so this should be 91.6 kilojoules. Yes, 91.6 kilojoules are released. If this reaction releases that, that's why it's negative, because the system itself has released some amount of energy, so it's negative 137 for this reaction. So it is released. If you put 3 moles of NO2 in here, it would release 137 kilojoules. But we didn't put 3 moles in, we put whatever 92.3 grams whatever that is in moles, so we got something other than 137. The only other way you'll see these is instead of being given an amount of a reactant or a product, you're given the energy itself. This is saying 1.24 times 10 to the 5 kilocalories. So calories and joules are the energy units. You can convert between the two, but I didn't give you any questions like that. So this one, how many moles of propane will burn? Propane is a C3H8. So 1 mole of C3H8 is 531. So as far as units go, I would write that. And then it says, how many moles of propane? Okay, actually moles of propane needs to be on top. I'm just gonna say propane. See, there you go. What am I doing? 1.24. That'll do it. Kilocalories will, I'm gonna do 1.24 divided by 531. Times 10 to the 5 moles of C3H8. 10 to the 5, let's do 10 to the, well, okay. 3 significant figures, 3 significant figures, so I'm keeping those 3. So let's clean this up. 4, I'm rounding the 3 out. And if there's an answer in there, let's go ahead and, out of these 5, let's go ahead and do 1, 2, 3. That should be the answer. Oh, that's fine. I guess we go ahead and complete, can't calculate by 2 more there. That's the answer they have. This is in scientific notation, standard scientific notation. This is also correct. All 3 of these are 100% correct. This one's in standard scientific notation. This is kind of a natural way you might write this rather than use standard scientific notation. That's the most painful one to look at, but they're numerically equal to each other. So all 3 of those answers are correct, unless you're asked for standard scientific notation, in which case it would be the middle one. We have 4 minutes. You want to run through, the rest of these are conceptual questions. Energy and reactions. Exothermic, endothermic, stuff about the reaction diagram. So C is the transition state, E is the reactants, D is the products. Do you remember what A is? The distance from the energy where the reactants start to this peak is called the activation energy. Do you remember what B is here? The difference between where reactants and products are is the delta H, also called enthalpy, but I don't think your book used that word. But that delta H number that I was pointing to for the kilojoules, that's the delta H. So for this type of stuff, if I'm not going to go over every detail in it, Let me just point in the book real quick before y'all leave. Most of that